Lenz's law. Now it's time to explain the minus sign in Faraday's law. It's so important that it has its own law. The minus sign tells us that the direction of the induced EMF in a current loop, again induced EMF, is such that the resulting current will produce a magnetic field that resists the change of flux through the loop. This is a direct result of the law of the conservation of energy. We'll talk about the conservation of energy later, but let's now just figure out how we can mechanically handle this. If the external field that's generating the induced current gets weaker, the induced current doesn't like that. It tries to replace the missing field by generating a magnetic field to replace it. If the external field gets stronger, the induced current opposes that. It doesn't like change. It will generate a magnetic field opposing the change. And the key right here in the italics here, only the magnetic field within the loop, the magnetic field that is generating the induced current, counts. Disregard any magnetic fields outside the loop. Just count the one inside the loop. First of all three of these wire loops are the same loop. It's just over time. That's different time snapshots of them. First, here's our loop. We have an initial external field, an initial magnetic field which is coming out of the page. Then we turn it off. So our final condition is here. There's no external field. So the magnetic field changes, so the flux changes. That will induce an EMF in the loop that will generate a current in the counterclockwise direction. Why counterclockwise? Well, here we had a field coming out of the page, then we have no field. This loop wanted to keep that field, so it's going to generate a field coming out of the page. We then use the right-hand grip rule. We put our thumb, we choose one way or the other. If we choose this way, we put our thumb into the page, along the wire, we curl our fingers, and we find that they're coming out of the page within the loop. So that's the correct direction for the current. That's why it's counterclockwise. If we had guessed the other way, and that's fine, you would have put your thumb going this way, okay, in a clockwise direction. When you curled your fingers in, that would create a magnetic field like this. Now, of course, outside the magnetic field would be here, but we don't care about what's outside. We just care what's inside the loop. Since we had to regenerate or attempt to regenerate this field, this is the correct choice, so it's counterclockwise. This time, we start with a loop with no external magnetic field. Then somebody turns one on, and this magnetic field is coming out of the page. We know this will generate an EMF, which will then generate a current, but it has to oppose this increasing magnetic field. How do you oppose a field coming out of the page? Well, you create one going into the page. So you use the right-hand grip rule, and I'm just going to guess right the first time. Put your thumb in this direction, curl your fingers, and see these X's here? You're generating a field into the page which will oppose this change. So in this case, the current is clockwise. We haven't actually shown the negative sign yet, but what we're talking about is the negative sign implies that the current is flowing in a direction that will generate an opposing field. And opposing, another word for that is negative. Here's a summary. The magnetic field due to the induced current, okay, that's the second magnetic field you have. That's created by the current that was induced. It will point in the opposite direction to the external magnetic field if that field is increasing, because you don't want it to increase. You want it to maintain the status quo. It will point in the original direction of the external magnetic field if it is decreasing. You want to restore it. And again, it will be zero if the flux is not changing. And that's Faraday's law. There is no induced EMF if the magnetic flux is constant. Remember, big remember here, the external magnetic field that perhaps you're controlling by switching it on or off is different from the magnetic field that is created by the induced current. Two different magnetic fields. You may have actually seen Lenz's law in operation. Have you ever noticed that when you unplug an appliance that is running, there is a spark that jumps between the wall socket and the plug? Here's the spark. This is explained by Lenz's law. As the plug is pulled out, the current is decreasing, which collapses its magnetic field. This change in the magnetic field induces an EMF, which produces a current which is seen as a spark. This is one reason why you should always turn off appliances before you unplug them. The energy that was stored in the magnetic field transformed into the electrical energy of the spark.